Zener regulated power supply using the following parameters. We have an unregulated input voltage of minus 26 volts plus or minus 10%. We have a regulated output voltage of minus 22 volts, and we have a load current between 10 milliamps and 15 milliamps. Probably need to get you a computer because we got to look up a data sheet. So we're looking up in the 4700 series of Zener regulators, we're looking up one that's got a regulated output voltage of 22 volts. Which one we use? So, I'm sorry, data sheets. And then the 1N47 series, 700 series. Then we're going to look for a data sheet that's got yeah, that's the very first thing. It says all of these. If you look at the very first part of it, it says use the appropriate data sheet for a 1N4728 through a 1N4764. So we have to figure out one. So we're looking for one that's got a VZ at 20 volts, which is the one. Oh, I need to turn on the projector. Okay. So we're looking for a 22 volt VZ, and then we're looking over for the IZK, the knee current. Are we okay? There's no such thing. Zeners don't look at negative and positives. We put it in the circuit, reverse bias, period. Right? You understand? So Zener's not rated at negative. They're rated over breakover voltage. It's up to us to decide how we put it in the circuit. We put it in the circuit, reverse bias. Understand? I knew that question was going to come up. 4748. And then an IZK of 250 microamps. So our circuit over here, we've got 26 volts coming in, so we'll draw the circuit. We got RS is right here. That's what we got to calculate. We'll put my Zener in this direction right here. And this will be my common. So notice I got the anode pointing toward the what? Toward the negative. And then my load is going to connect over here. We're not even going to draw the load because it could be anything. We don't know what the load is. All we know is its current's going to vary between 10 milliamps and 15 milliamps. It could be a light bulb. It could be anything, right? You understand? So we don't normally draw the load on power. So this gives us a negative regulator. I've got a negative, I got my anode point on the negative, so now our circuit is set up correctly. And then my input voltage will come in right here, and my input is going to be varying from 26. So let's calculate VN max, and we'll calculate VN minimum. So what would that maximum be? 28.6. Here's the worksheet. They decided to work. They decided to work 3. Mm-hmm. And I think this is the only negative regulator in the whole thing. So what's V in maximum? What's that? 28.6 minus 28.6. And what's our minimum? And guys, we're through with signs from now on. Signs have nothing to do with the rest of the calculations. So from now on, we're going to use absolute values. I understand that, or integers. So we need to calculate VRS minimum. All right, we'll do it. I need to put them in the same order. I guess. So we'll calculate VRN maximum, VRS max, and we'll calculate VRS minimum. So what's the maximum voltage VRS would have to drop? So I've got 22 volts on this side. I've got 28.6 volts on that side, or I could have all the way back to 23.4. So what's the maximum is it going to have to drop? Well, the maximum it's going to have to drop is 28. Kirchhoff's voltage law says the sums of the voltage drops in the circuit, the elements in the circuit add to the applied voltage. I got 22 on this side. I got 28.6 on that side. 22 on this side, 28.6 on that side. How much does the resistor have to drop? 6.6 volts. Is that a minus or a plus? It's a voltage drop, guys. It don't make any difference, right? You understand that. And then what would my minimum voltage be? Well, it's going to be equal to 23.4 minus what? 22. Huh? 1.4. And now we've got basically all we need to calculate the whole circuit. So I didn't bring up the standard resistor chart. I should have ran that off for y'all. So you'll need to look that up. And we'll choose the 5% resistor because that's the most widely used, right? Okay, so what are we going to calculate next? Yeah, the size of that resistor. So if we look at our formula sheet, what's the formula for calculating RS? So we got one that's called Zener regulated power supplies. That's in our formula sheet. And there should be one called RS. Calculated. It's not chosen. This is calculated, right? You understand that?
RS?
Yeah.
RS equals V RS minimum over IN max.
The RS minimum. I'm not going to write the formula. I'm going to write the numbers. Because I will run out of room. So VRS minimum is going to be equal to 1.4 divided by what?
IO max.
You got 15 milli plus IZK,
Plus 250
not milli, micro.
million.
This is an EM. This is micro. I don't know how it looks like an EM. I mean, it might look like your EM, but that's.
I might keep my glasses.
So calculated, this is VRS calculated. This is not what we're going to use, right? You understand? This just gives us a shot. What'd you say?
I had 93.3 micro.
You got that right. I can't be. There's no such thing as a 93. And you got to understand, resistors are never going to be in microohms. So if you come up with microohms, it means you had to do something wrong, right? Okay. And then you just got to come back and figure out what in the heck did I do wrong. The biggest problem people have is not understanding that they got to use parentheses. If you don't use parentheses, you're going to screw up. So I'm going to say 1.4, and that's why I drew it down there, 1.4, and then I'm going to say divided by, and then I'm going to open up parentheses on my calculator. If you don't, you're going to end up multiplying by 200. You're going to take your answer and multiply it by 200. So this is 15 milli. Yeah, and that's what I'm saying. You know, there's no such thing as a micro ohm. A micro ohm resistor would be a fuse, or something like that. So, oh yeah, so that's and then we're gonna multiply that by 250 micro, right? Oops, crazy, dang it. Sorry, I probably lost everything. 1.4. So what do we got? Divided by 0.015 plus, yeah, 250 micro. Close my parentheses and about 92. Or 91. And what we do with Zeners is we always go down. We don't ever round up. We always go down, right? Understand that? But if you chose it, you should still get the right thing. So 91 ohms, 92 ohms. There's no such thing as a 92 ohm or a 91 ohm. Huh? There is a 91, but I know that's going to be wrong. Huh? Yeah, tolerance is going to take us right out the back. And this is what I told y'all. I said, even if it falls right on a calculated resistor, you might as well do what? Go down. Yeah, you might as well, because once you do the 5% tolerance, then you got problems. So what's the next one down below that? Okay, so we calculated 91 or 92, and then we can say, then I'm going to say 91 times, then we choose a what? What's the next one? Huh? 82. And then I'm going to multiply it by 1.05. And that gives us 86. And that's lower than 91, so that means that's going to work fine. So 86 looks good. Looks good. Okay, guys, what we need to do next. I'm going to a place up here that sells resistor. And we're looking for what? An 82 ohm resistor. And these are all 82 ohms. Let's go, so what's some of the things we need to specify? We need to specify the wattage, right? You understand? So when I buy a resistor, I got to specify two things. I got to specify the size of the resistor, and of course the wattage, and of course the speed. Look, carbon resistance, 82 ohm, half watt, 5%, bag of 100. Right? 0.5 cents a piece. 5 cents a piece. So like I said, we could use a rheostat and get whatever resistor we wanted, but that would be a waste of money, right? So we're going to use a standard value. So what's the wattage rating? So we're going to come up here, and what's the formula we probably need to use? There's several formulas you could use. I'm going to put the maximum voltage, because it's going to dissipate the most power when it's dropping its maximum voltage, right? You understand? So I'm going to put 6.2 squared over the size of the resistor that we chose. And this would be PRS. B squared over R. Is that what it shows on the formula sheet? Huh? Oh, I don't know. How did I come up with 82? Oh, okay, my fault. I see where I pulled it up from. I pulled it up from our tolerance. Sorry, guys. I was just seeing if I was paying attention. So what's the wattage rating we need on that guy? Now this is what we're going to calculate. We'll calculate the actual value, but what would I buy? Okay, so now what do we need to do? We could, but what we're working for is we're working to see if we're going to burn our Zener up, right? So we're going to make sure we're not going to burn our Zener up. So what we'll do to calculate the current flow through the Zener is we'll see the maximum current flow we'll have through our 82 ohm resistor. We'll subtract from that the current flow we have from our load, right? So PZ would be equal to the Zener voltage, which is 22 volts, times, we could do this with one whack, but 6.6 divided by 82 minus 10 milli in one formula. I think it shows you to calculate RS minimum and RS maximum. Either way, this is going to be RS maximum right here, right? Minus this, this will give us the current flow to the thing. So whichever way you solve it, you find. How does it show it on the formula sheet? Yeah, well, see, that's what I'm doing. I'm just doing it in one formula, right? Does that make sense? Does that make sense, Gilbert? So if I was going to calculate RS max, I could tell you didn't. Max I would take, would be equal to 6.6 volts. That maximum voltage divided by the size of the resistor. Well, that's what I'm doing right there, right? You see that? Can't see my period right there. So what would be my maximum current? So I could do it with one whack over here. I could say 6.6 divided by 82 equals minus 10 milliamps times 22. So I could work through the formula backwards and do it with one formula, right?
I thought you did two formula 24 just insert into the book. I got you.
Yeah. And that's the way I see it in my head. So what would be the power for the Zener? Maximum power that this guy's going to dissipate. What we got? 1.5. I don't know. Huh? What's that? Okay, so the formula says PZ is equal to VZ times IRS max minus I the load minimum. Okay, so what's RS max equal to? It's going to be equal to the maximum voltage that resistor would ever drop, right? You understand? Divided by the size of the resistor. Ohm's law says I is equal to V over R. If I'm trying to calculate the maximum that a resistor will ever drop, I'm going to use the maximum voltage that it'll drop, right? You understand? Okay. The maximum voltage it would ever drop divided by the size of the resistor. Okay. So what's the maximum voltage it would ever drop? 6.6. What is the size of the resistor that we showed? 8.2. So the formula says IR max, right, minus I load minimum. Well, all I did was take that formula and stuck it inside here. So what I'm doing is I'm calculating IZ max, I'm calculating IRS max as part of my formula. So here I've got one formula. You don't have to do it, guys. You can work it out the other way. I can say 6.6 on a calculator. I can hit this with one swoop. I can say 6.6 divided by 82 minus 10 nearly times 20 equals. I have to equal times 22, and I'd be through with how many formulas. It's one formula. So let's see if we come up with the same thing. So I'm gonna come over and pop up my calculator, and I'm gonna work it this. I'm gonna work it this way. I'd come over here and I would say 6.6 divided by 82, right? Then I'd say equals minus 10 milli equals, and then I'd say what? Times 22. I'm sorry, yeah, 22 equals 1.6 watts. So what does that mean? Oops. Yeah, it's over 1 watt. We'd burn our Zener up. That's exactly right. So what would that mean? Huh? So I'd come up here and I'd say, I'm looking for a 2 watt Zener. 2 watt, what? 22 volt Zener. Or we might. Because we can't use this Zener. All these Zeners are rated at 1 watt. You can't change the Zener because I'm looking for a 22 volt power supply, right? You can't change the size of the resistor. If we go up, we won't be able to get the current specifications that we're going. If we go down, we'll burn the zener up anyway, right? You understand that? So the only options for this design, this is what I'm doing, and this is what you do when you try to build a power supply. What's the first things you're going to look at? If you're going to build a power supply, what's the first things you need to know? What voltage the load requires and what voltage the current requires. Because what's a power supply built for? It's not built to just be a power supply. All power supplies are built for one thing, and what's that? To run a load, one or more loads. That's what they're built for. So that's the first thing you would need to do. You need to watch. You need to know what load. So this computer has a battery in it. What decided what battery that they put in there? How they went in and they figured out all the devices inside that thing. How much current does it require to run that? And then they figure out how long do we want to run it, because the batteries do what? They discharge all the time. But when I chose a power supply, what did they have to do with that power supply? This power supply not only has to have the ability to charge the battery, it's also got to have the ability to run the load too, right? You understand? So I can unplug this battery and plug in this power supply and still turn my computer on. So not only does this guy have the ability to charge a dead battery, it's also got to be able to run the load while it's charging the battery. So when they engineer these things, that's something you got to understand. Now, right now we're dealing with little Zeners. Zeners work great as long as I don't demand. Look at our current loads, 10 to 15 milliamps. So Zeners are not designed to run a big load, but they're very cheap and they're down and dirty. So if I've got a load that doesn't have a big milliamp requirement, then I'm not going to go out and spend $5 on a regulator, right? You understand that? To run a very small load, I'm going to use a Zener. And then we'll show y'all real fast where we could add a transistor to this thing and get a lot of current out of it. And it'd be a lot cheaper. So you're going to run into Zener regulators. In fact, I could look at this guy right here, and I guarantee you there's a Zener in the electronic circuit somewhere. So even most regulators use a Zener just to establish a reference. So Zeners are real neat. And the biggest problem we have is people don't understand that the dang things have got to be put in the circuit what? Reverse bias. So if I've got a minus, I point the anode toward the minus. If I've got a plus, I point the cathode toward the plus, right? And normally we don't put the load because all we're saying, I don't say what type of load it is. We just say this would be the output of my regulator. This would be what? The input. And there's the Zener circuit. So all your Zener circuits are going to look about the same for all these worksheets. Well, basically, all you're going to do is swap the direction of the Zener depending on it's a what? A negative or a positive supply.
What's the difference?
No, it's not. It's a positive supply. So when we say it's a negative supply, the positive is common. And you're saying, oh, you're trying to put the negative common. If you put the negative common, then it's not a positive supply, and it's not a negative supply. It's a positive supply. You understand? So as soon as if I came over here and did this and swapped this around and made this positive, my Zener's forward biased. And now it's not a Zener, it's a diode. It drops 0.7 of a volt, right? You understand? So when we talk about a power supply, and this is the problem in DC, all you do is work with positive supplies. And you don't understand, why do we need negative supplies? Well, there's electronic devices. When the FETs first came out, they required negative supplies. You had to have a positive supply and a negative supply. But how can my stereo in my car generate an AC output off of 12 volts DC? It's got to generate a what? A negative supply. You can't make AC with just a positive supply. You got to have both a what? A negative positive supply. So everything that generates an AC output is from a DC has got to somehow come up with a negative supply. So those inverters you buy for your car that you can run AC devices off of, somehow that inverter is generating a negative and positive supply, right? You understand? So it can generate AC. So we have negative supplies all over the place. In fact, this computer's probably got a negative supply in it. I don't know. USB is all positive. There's a less and less demand on a negative supply in a computer. Used to, we had a port called an RS-232 port, which to help it avoid ground shifts in the transmission, it used a negative and a positive DC supply. Because but anything, and it was I forgot what it could be. It could be up to like 20 volts. So the biggest problem we have with sending information over long distances using what we call single link. So we got two ways, and one way we used for years. We used it for years. It's where we would have one wire that we would call our signal wire. And then we had another wire that we established as a common or a ground. Now what was happening was we would come up here and we would get an electromagnetic pulse that would move through there, and it would generate noise in the signal wire, but it couldn't generate noise in ground because that's what it was referenced to, right? You understand? So, and this limited the length that we could send our information. So parallel was basically limited to 15 feet because of this garbage that would get in on our signal. So what they did is they came up with a method where they could use a negative and positive supply. And then another thing we have, if we try to send current through a conductor, then we get what we call line loss, or we get voltage drop in the wire itself, right? Does that make sense? So we were really, really limited on how far we could send these things, not only because they could pick up electromagnetic interference, but also we would have a voltage drop over distance. So they said, okay, let's come up with a technique where we'll have a 0, and then we would send a minus 15 volts, or we would send a plus 15 volts. But anything above plus 3 was considered to be legal. Anything below a minus 3 would be considered legal. But we'd send it at plus or minus 15 volts. So that means you could have a ground shift of a lot of volts and still do what? And still get legal data. And you could have noise riding up here on the 15 volts all over the place because it had to drop down below 3, right? You understand that? This is the way we send it for years using what they call an RS-232 interface. But it still referenced the ground. So what they did eventually is, once electronics came out, they came out with an amplifier that we call a differential amplifier. And what the differential amplifier would do is we would send the signals 180 degrees out of phase, and we never ever use ground. So we'd send the signal over here. This was the symbol for the non-inverted. So that's not plus. It's a symbol that what's a symbol? It's when you use something to represent something, right? So this is the symbol in mathematics. We use that symbol for plus. In digital, we use that symbol for an OR. In communication, we use that symbol for non-inverted. So we'd send a signal out here. I'm going to do AC. But what we'd do on this side is this one right here would be 180 degrees out of phase. So the minus represents what we call inverted. And then what the differential amplifier does is it only amplifies the difference. It does not amplify the voltage, it amplifies the difference. We'll find out who's unplugging my power cord. So what would happen is we'd get a noise pulse that would come through here, and it'd generate the pulse, generate that pulse there. These is what became known as common mode signals. And what would happen is the differential amplifier only amplifies signals moving in the opposite direction. So what would happen is over here, we could convert it over to a single-ended signal that had a really big, what they call a common mode rejection ratio. So you'll see a CMRR, which they call the common mode rejection ratio. We're talking about 30 dB. 30 dB, which means it would block out only 1/1000th of a noise had a basic possibility to get through. So how would I generate differential signals? Well, or how would I do this? So what we're saying is that there's always a need somewhere for negative power supplies, right? You understand that? And as long as I don't have a high current demand off of these things, then, you know, we'll use Zehners to get these things. If I have a high current demand, then we're going to have to add more electronics to it. And I was to look at the data sheet for a 3-terminal regulator. Guess what you're going to see inside that thing? If they show the schematic. If it's a voltage regulator, I guarantee you there's going to be Zehners in there somewhere. Did I show y'all that? So this is a variable regulator, an LM323. Let's see if they got the schematic in here. It didn't show up real good. So there's a Zener right there. Here's a 6.2 volt Zener right there. There's a 6.2 Zener right there. Now the circuit itself is very, very complicated, but we don't have to worry about it. And why is that? It's an integrated circuit. All you got to do is worry how. So I got an input on the left, I got an output on the right, and then I got a water common. So this is going to come in a 3-terminal case. Let's say it's either going to be in a TO3 or a TO222. What I've also probably put up on there is on the data sheet is these different cases, these different standard device outlines, yeah. And then they give you pictures. So a TO22, the one at TO22 is that was not. So a TO202 would look like this, right? And then a TO3 would look like this. We'll show y'all some of those. TO stands for transistor outlines. These are all open technology by the Joint Electronic Device Engineering Council, or what we call JEDEC. And they come up with these standard outlines. Now, why do I need a standard outline? What's so nice about standard outlines? Well, these guys have got to plug in the circuit boards or do something somewhere. So if I was a manufacturer and I came out with my own pin out and had my pins arranged in whatever way I wanted to, then nobody would buy them from me because they would have to buy everything from me. They don't do that anymore. When electricity first started coming into homes, and you wanted to buy an appliance, different houses were wired different ways because there was no standard out there, right? You understand, different plugs. Well, NEMA, the National Electronic Manufacturers Association, started standardizing plugs. So now we got standardized plugs. They came up with standardized mounts for motors. So when you go out and buy a motor, you know what NEMA frame it's got, and you can buy a motor that's got the same NEMA frame, and you know it will do what? It'll mount on it'll mount on your pad. So that's very, very popular in this is these standards. So standard plugs. These guys on the wall back there, those are NEMA plugs. Those are NEMA 520s, 20 amp plugs. That's a standard plug, right? You understand? So now I can buy a standard a plug that plugs into that thing, right? You understand? So maybe if you take, I think residential wiring, they show you all the NEMA standard plugs. So that's the worksheet. We're gonna make this due when? Tuesday. You got something to do during the weekend. There's something else I needed to show y'all on the data sheet that I forgot. So we see some notes down here. Let's look. This is the one we're going to look at. I'm looking at note number 1. This is not. So we know that every electronic device that we have probably has a tolerance, right? So it says tolerance of type numbers designation. JEDEC type number listed as a standard tolerance of what? 10%. So standard tolerance of plus minus 5% on individual units is also available, indicated by suffix and to the standard type number. So that means if I got a which one did we choose? 22 volt here. So a 1N4748 would have a plus or minus 10%. A 1N4748A would have a 5%. Y'all understand that? That makes sense? Yeah, I think these are the Zehners that we're going to use. I think we got 47. Yeah, I know we do. So we're going to have a lab on this. It's going to be a handout lab.
I'm not over here, so for the worksheet, what made us use 4748?
We were working on circuit number 3, and it says we're trying to generate a 22 volt power supply. Are you looking at the worksheet?
Mm-hmm. Okay.
So we chose to put 1N4748 because it's the 22 volt Zener. So that's what determines. So your output voltage that you're looking for determines which Zener you're going to choose, right?
Yes.
So the first one we use the top one we use we're looking for a 5.1 volt power supply. So I would use a 1N4733, right? You understand? And Zener voltage has nothing to do with whether it's a negative supply or a positive supply. Zener voltage, it just tells you where it breaks over. What makes it a negative supply or a positive supply is how you bring your input on, and then of course you got to put the Zener in there. What? Reverse bias. That makes sense. Okay. So guys, let's go to lab.
If I need it, you know, right?